All right. I just need real quick to see if my mic is okay, because this morning when I recorded it was super hot and it kept clipping. So is microphone okay? Whoops. Let me know if it starts getting choppy or if it starts getting stuttery or if it starts clipping. I've got it turned down, so but I don't want to turn it down too much to where you can't hear me. So if at any time the voice gets scratchy, let me know, because I want to notice what I'm doing when that's happening. Okay. All right. Let's go ahead and get started with chapter 4. And this is all about programmable logic devices, CPLDs, FPGAs, which is what we're using. And then we'll talk about VHDL design, even though we don't use VHDL in our digital classes here. Okay. So, a PLD, or a programmable logic device, contains thousands of basic logic gates in a single package, and that's that chip that you buy. In our case, it's the I'm blanking the new one. I don't have it memorized yet. The DAF 10M50 DAF 484C7, I think is what it is. Thousands and thousands of basic logic gates in that PLD, okay? And when you create your VHDL file or when you create your BDF file, essentially you're telling it what to do. You're saying grab a few of these gates that you have here and make these connections internally. So that's what it does. You download your program, it makes the internal connections, it takes the inputs to the switches and takes the outputs to the LEDs or the 7-segment displays or whatever. And so it does it all automatically. So instead of having to wire up an incredibly complex, maybe you're using 14 or 15 IC chips, okay? That's a lot of wiring that could go awry, all right? So if you have it all laid out in something like this, just to try to test it out, because if you're going to try to test it by actually physically building it, you could waste half of your time troubleshooting. Now, that may happen anyway, but you at least want to be trying to achieve a design that you know is good, that simulates good, that has been proven in the software, okay? So put it all into the software first, and then you can, if that checks out and everything simulates okay, and you send it down to the prototype board, and the prototype board is okay, now you can go ahead and start milling your PCB boards and creating a circuit that's going to have all the physical chips on there. Okay. All right. So, when you hear the word CAD, and you may have heard the term AutoCAD, for instance, okay? The CAD part of any of that just means computer-aided design. That means if you take 111, Multisim is a CAD program because it's a computer-aided design for circuits. Quartus is a CAD program. It's a computer-aided design program for digital circuits, okay? AutoCAD is what mechanical engineers use to do their 3D modeling, okay? All of it is CAD, though, because CAD just stands for computer-aided design. So we are using the schematic capture. That's where we enter on our gates, and we put in our inputs and outputs, and we make the required connections, and it'll show us where on the BDF file that we have these attached to address-wise in terms of the switches and the LEDs. Okay, it will also show us, like I said, the pin assignments. So we get the nice option to have all of that in graphic form with the actual what an AND gate looks like and what an OR gate looks like. The computer doesn't know what any of that stuff is, though, so it has to convert it all down to ones and zeros, right? Essentially hex byte instructions, right? And so another way to do it, if you're not going to do the schematic capture, all right, you can do it in VHDL. So VHDL stands for a really, really long acronym, because the V is an acronym itself, and it's I can't remember, very high something IC hardware description language. Okay, oh, there it is right there. Very high-speed integrated circuit. I could never remember what this part of it is because I only remember the hardware description language from VHDL. So anyway, we will not be designing in VHDL, but if you know how to do C, if you know how to do C++, or if you know how to do Java or any other programming language, you can teach yourself VHDL, okay? Now, when I show you an example of it, I'll point out how I believe it's kind of clunky, and I don't particularly care for it. And I know a lot of different programming languages, and this is probably my least favorite. I would much rather program in C, like to a microcontroller, than have to do it in VHDL. But you know, if you can teach yourself VHDL, that's just one more thing you can put on your resume. Okay, and you know, like when Professor Atkins worked at, I think, IBM and Intel, they used something similar. I don't know if it was VHDL, but instead of doing schematic captures, that's what he would do, is he would just write scripts that would try to execute these new circuits they were coming up with. So let's see here. So here we go. So this says implementing the equation x equals, okay, so we got a little bit going on here. X equals, this is the single inverted A, right? Not both of them together, but single inverted A and B. So not A and B is how I would read that. So x equals not A and B, or, and now you see the bar is over all of this, so that's a NOR, right? You take the OR of the two together, and then you invert the output over the whole top. So, you know, x equals A naught and B, or B plus C prime might be a way to say that. Or you could just say B plus C, the whole thing knotted, which is not the technical term, but I think it explains it better. You know, B plus C, the whole thing knotted, okay? So if you were going to implement that with IC chips, you'd need to have, well, you'd have to have something for an AND, right? Because there's an AND right here. You know you're going to have an OR somewhere, and this one is a NOR. And on top of that, you have to invert a single input here. So you're going to need 4 separate types of gates, which means you're going to have 4 separate IC chips. And you can see, you know, again, I'm not going to quiz you on, if I ask you about one of these, I'm going to give you the pinout, or, you know, you have your book, you can find out what the pinout is. But anyway, here's the bank of inverters on the 7404. Here's the bank of AND gates on the 7408, NORs and ORs. So here's one of the inputs, A. Before you get to the AND part of this, you got to send A through an inverter first. Okay? So that comes up here then to pin 1 after it's been inverted. B can go straight into pin 2 right there. They get ANDed together, and it gets outputted at 3. Okay? Now you're going to take that thing and OR it with something. OR it with this NOR. So this 3, if you follow it all the way around, gets connected up here at the first pin of that final OR gate. So now this part of it, the B or C, the whole thing knotted. So here's B. You can follow it. It gets tapped in at 2. That's one of the inputs. C is on 3. That's another input. Notice how the pinouts change depending on what gate you're using. Okay, so it's not always that 1 and 2 are inputs. Sometimes it's that 2 and 3 are inputs, right? You always have to know the pinout before you start making connections. So C gets connected to 3. The output of that is now the second input on this OR gate. And then you OR those together, and then out comes X. Okay? So that's, you know, and you got to remember, on top of all of that wiring, you also have to have a ground here, and a ground here, and a ground here, and a ground here, and power, 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 and that power is 5 volts. So you'd have to attach 5 volts on top of that to each one of those chips to power them, and then put a ground on pin 7 to ground them all, so that they'll work. So if you don't power them up, then they won't perform this function, whatever the function is they're supposed to do. Okay, any questions on that? If I could spell it right. All right, Making sure that I just popped out the chat to make sure I didn't miss anything. Okay. Now this is an example of a different type of Altera chip, a Max, whatever this is. And so, you know, the way that you would orient this to know whether you have it in the right orientation of where you start counting, there's a little notch in the left-hand corner here. And so you would orient it so where this is in the top left of, you know, how you were looking at it. And more than likely, it's going to be printed on here just like this if it hasn't rubbed off. And so you can see which way it should be facing. Okay? And then just like all the other IC chips, it's got a little notch that indicates where pin 1 is. And then it just goes counterclockwise all the way around. Now, you know, when we go, if I switch over to my desktop real quick. So when I say pin B8 and pin A7, what I'm talking about is something around here, right? I have to know which switches are connected to this main chip. And then this chip will make the internal connections between the inputs and the outputs, right? Because you know, this one is at pin 73, wherever that is, whatever that is. So that's what's going on. It's got all the inputs connected in these places around on one side. It's got the outputs on the other. And then, you know, there are other signal pins that are attached to this as well. Okay, so like I think our boards will write to Arduinos. And so you got to have something that ties into the outputs here that sends it to the Arduino so that they can talk between each other. So that's outside the scope of this class. But anyway, that's how it's kind of set up. So if you look at your board, I can pull my board out here that I've got. And, ooh, this one shows where the notch is supposed to go in the top left-hand corner. If you look at your chip, and so right now I'm looking at, let me pull back here to, so on the board itself, if I'm looking at it where Altera Max 10 is right side up and not upside down, you see in the top left-hand corner, there's a little bitty yellow triangle. So when you're assembling this chip, that's where that top left-hand, you see where there's a little, you know, there's the little tiny yellow triangle up in the very top left-hand corner. And then on the chip itself, there's a little, I guess that's like a gold dot or whatever. So those have to be in the same place before you put the chip on here and then it gets soldered in, right? Obviously, a machine is the one that did all this. You see how small the components are. There are people out there that could solder this. I could probably do it, but it would take me, who knows how long it would take me. I wouldn't even want to do it. I don't know if I would, how much I would charge for something like that. But anyway, there's so many tiny little pins on there that a robot, you know, automation has to do that. But anyway, you can see how it's oriented there on the board. Let's see if I can make this look a little bit better here. There we go. It was cutting off part of the slide. That's no good. All right. So one type is called the SPLD, the Simple Programmable Logic Device. And there are 4 different types. Okay, again, the one that we use is the FPGA. Most basic, least expensive, configurable logic gates, programmable interconnection points. It's basically restating everything I just said. Memory flip-flops so you can store data. And ours has, it says typically 16 plus complements and 10 outputs. We have, oh geez, we have 10 switches. We've got 10 LEDs. The school boards have, I think, 36 LEDs. They have 10 and 8. Or 10, I can't remember what the exact number is. But we also have these 7-segment displays that we can write to. Okay, those are outputs also. So it just depends on what you buy, right? We also have 2 debounced push buttons. And so you can break it down even further, a PAL or a PLA. And so essentially the output of this will be a sum of products form, which we'll talk about in chapter 5 when we talk about Boolean algebra. So don't worry if that doesn't make sense. Think about this in terms of algebra. Okay, so that would be the quantity A plus B. It would be AB plus CD plus EF, the sum of products. Okay, a programmable logic array, if it's backwards like that, it's a sum of both of these are sum of products form. Okay, if it was product of sum, which will become relevant in chapter 5, I apologize. So when we talk about that in chapter 5, it's going to be the opposite. It'll be quantity A plus B times quantity C plus D times quantity E plus F. Okay? So both of these will give a sum of products form, and that's what we're going to reduce everything down to in chapter 5. So that's why what we do with the BDM, the PDF files, why we're able to do them so easy once we get our equation down to essentially a sum of products. Okay, it makes it super easy to wire it. And we don't know what flip-flops are yet, but those are what allow us to actually store, if you get an output of 1 from an AND gate, how do you store that and use it later if you want? Okay, so flip-flops allow us to have memory that we can store the state of any output. Okay. I'm not going to get into the naming of this. Just want to introduce the different types here. Another type is the complex programmable logic device. And so essentially you have a couple of different Arduinos on the same board. So you can write gigantic programs like, if you're doing manufacturing of some type of digital device, then you're using something much more complex than what we're using. So you're probably using something like this. Here's the other thing. If it is complex like that, you probably want to retain what you have on there. When you download your program to our board, as soon as you remove the power, it's gone, right? Our memory is volatile. But we don't do anything complex. It takes no time at all to download another program if we need to make a change. So these are non-volatile memory. So if you are working on it late at night and you put it down and just unplug it, when you come back in the morning and plug it back in, it will fire up with what's already in the memory. So it's non-volatile. You can retain, and so it more closely mimics what you would use if you were going to create some device potentially. Okay. The FPGA, this is what we use. It's the Field Programmable Gate Array. And again, the Altera Cyclone series is a good example. More dense and faster than CPLDs. I mean, I don't have my, I think I have, I've got a ruler or a tape around here somewhere. I always do. I got 15 of them. So this is almost 4, so call it 4 inches by 3 inches. That's how big this board is, and we have all of this stuff that's on there. I mean, it is just jam-packed on here, and in such a tiny little space to have all of that power. It's really, really great. But again, volatile. Programming is lost when the power is removed. So those, I ask those type of questions all the time, like on quizzes and exams. Okay, ASIC stands for Application Specific Integrated Circuit, used for large quantity demand. It says after testing on FPGA design after testing on the FPGA design, which is what we use, then you transfer it to an ASIC. Okay, and so like it says, Application Specific Integrated Circuit. So it's designed specifically to further test this initial design. This really is like the initial prototyping stage right here with the FPGA. Then you have something that gets transferred into a slightly more permanent situation here that's specific to whatever project that you're working on. And again, non-volatile, so it's programming is not lost when the power is removed. Okay, this is super helpful too if it's pin compatible with the FPGA, because then you don't have to write. All the pins are assigned on our board for what they are, right? And that's what the manufacturer came up with. Well, if we wanted to transfer that to an ASIC, we may have to readdress all the inputs and outputs to whatever this is. So it's nice when you can just transfer the whole thing over and then all of the inputs and outputs lined up. So again, there's a couple ways we can do this. We're going to use the schematic editor, as you know, because I've already done a couple of videos on this. But there is a VHDL editor where you can actually write out and define in VHDL your logic. There's a compiler. We talked about what that does. It takes your words and it takes your programming and it takes your schematic and it converts it into a big string of ones and zeros that the compiler understands as instructions. Okay? And we also know about the waveform simulator, which is, if you don't want to go ahead and address it all the way out to the board, if you just want to check to see if your logic is okay, right? You still could assign like I did. I assigned the pin to the wrong, or I assigned the output to the wrong pin, the wrong address, right? So you wouldn't catch that kind of a mistake in the waveform simulator. That's strictly for if you want to check your logic operation. Do I have everything compiled correctly? Do I have all my connections made properly? That's the kind of thing you'd use the waveform simulator for. So typically the operation is you get the schematic capture and you compile it in the schematic editor. Then you go over to the waveform simulator and you can put in different test inputs like we did, and you can test to see the logic portion of it. Then you can go ahead and address it to your board itself and actually wire up physical switches and LEDs and check the operation there. Okay, so it's kind of a three-stage process, and most of our labs walk through that same process. Okay, so again, compile and synthesize. Essentially, it's converting all that stuff into ones and zeros, regardless of how it's pulled in, because that's all that the computer part of it understands. So again, there's a basic logic design here, and I pointed this out in my so Steve asks, all these schematics are on that link you shared in Zoom? The schematics. Are you talking about the pin out of the device? So Steve, which schematics? Okay. So again, if you put these nicely on top of one another, the distance between them is the exact distance of the inputs of a 2-input gate, let's say, or a 3-input gate. So you could stack 3 on top of each other and they all should line up. Okay? So you don't have to do it that way. You could have one input that's up here and one input that's down here, and you could have crazy lines that, as long as it all makes its way back over to the input, it's fine. Okay? Because it's no different to the compiler as if it takes that big long path, or if it's just connected like you see here, right? That's just for your eyes only, right? If it knows this is connected to this, then it converts it into a string, and it doesn't matter how long that wire is. Okay, let me jump back over here, see. Oh, the pinouts, yes. It should be in the, I don't know which one it's in. It's probably in the video where I talked about Quartus. I believe I have that in the description. If it's not there, I can put it there. Okay, and I can put it in this one too, for that matter. Okay? And it looks like, boy, this is all wonky here. Let me see if I can pull this up just a little bit more here. Geez, it was cutting off quite a bit there. And on the sides too. There we go. I should have all of it now. Okay. So this is VHDL, and it's kind of similar in how you would set up, say, a C++ program where you're including all of your libraries at the top. You've got all your preprocessor directives before that, like in C++ or C or whatever, right? And then here's what I'm going to use in this program. And so there are a lot of different libraries that are available. You only want to include the ones that you need in the program because they can be quite big. And so you don't want to make this program any bigger, because if you include that, if you include another library that you don't need, that's just extra space that's being taken up. So you want to try to make this as tight as possible, so you only include what you need. Then you have this what's called the entity, and this entity name is called figure 4_13. Okay? And what you're doing here is you're essentially declaring what your inputs and outputs are. So I have two inputs, A and B, lowercase a, lowercase b, and I have one output called X. And we're using standard logic for both. Notice that, for every open parenthesis, there's a closed parenthesis. For every, I guess that's all they use here. Every statement is ended by a semicolon. That's similar to C. I just don't like this orientation, and I don't like how you write the code down here, right? How you define the logic. Okay, I understand it kind of makes sense, but I much prefer just to do the schematic capture. So anyway, here's the architecture, here's the actual logic, and then here's the entity where you have your inputs and outputs defined. So, we don't go through this, but essentially that's what the computer is going to end up doing. Is it's going to create something similar to this when it goes to do the ones and zeros for the file that it produces to run. Again, this is an AND gate here, and so you can see if my cursor here was the cursor in, if I could drag that over, A or 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. So you can see here the output X is responding to this input, and it just gets repeated over and over. Okay? Now this next part goes into this Quartus 2 tutorial, and I don't know what edition this is from, but if you just follow what I did in the labs, you should be okay, because that's what I'm getting ready to do right now anyway. Okay, so any questions before I start Quartus and do another example? I'm going to go all the way to the board again. Okay. Anybody? Okay. Well, then let me come back over to my desktop. It's going to look crazy for a second while it's a little spun out there. So, okay. I'm going to keep this handy and keep this open. And I also want to start Quartus. Quartus is a pretty big program. Here we are waiting for it to start. Alrighty. So I'm going to go ahead, and I know I have a couple of these other ones here, but I'm going to go ahead and start a new project again. So new project wizard. Now, if you do have issues with this, again, I haven't gotten any more emails, so hopefully everybody's figured theirs out. If you have trouble, go back and watch the videos that I posted, the ones I uploaded, not the live stream, but the ones I uploaded, okay? Because those, I go through the different issues that you might face, okay? And you have to make sure you set it up. So, again, I don't like that it's stored right there, so I'm going to go find the folder I set up for this class, which is under C, right? Because I know I have administrative rights here. Remember, the Neos 2 environment is why it's causing an issue and not being able to write to certain places. So I did show you a command that you can run in your DOS to get rid of that. But if you just don't want to deal with that, you still want to run the commands on this, but there we go. So Now I'm going to create a new folder for today, and I'm going to call this Lab 1B Second. Okay, and I'm going to double click on that, and this is where I want to store my information. So under C, okay, I said I created this one because I didn't want to deal with the write issues to the folder that it defaults to. So there's probably a way to get into the settings and change what this default comes up as. But I'm not that worried about it. I'll just change it each time. The name of this project, I'm just going to stick with the name of the folder. So Lab 1B Second. Notice that the design file, or I'm sorry, the entity here is the same name as this. They have to be exactly the same. So then okay, so I blew right past that. Make sure this is still saying empty project. Don't choose project template. Skip the add files, and then we want to come to device max 10 DA, and scroll 10M50 DAF 484C7. There it is. Okay. So again, I only have the max 10 on here. You may have the other ones, and so you have to dial down into this one. So I'm going to click next, and then finish. And so if you get stuck right here, I'll just remind you, if you get stuck right here, if it doesn't go any farther, then you've got some type of a write issue, okay? Meaning it's trying to create files right now. You can see what it's doing. It just created that folder and a bunch of other stuff inside of it, okay? So if I go down here to C112, second, okay, see how it's already created all this stuff in here? If you haven't given it access, administrative access to write to this folder, then it has no way to create these, and so it gets stuck. It doesn't know what to do. It doesn't have a way to kick itself out, and so you have to shut the whole thing down. So if you get to this point, then you have access, and things should be okay, all right? The other thing, remember, that you want to check is if you go to Assignments and Settings, about halfway down is the EDA tool settings. The simulation here, you want that to be Model Sim Altera. Okay, so I say apply, and then okay. All right. So now I'm ready to go. I want to go ahead and create a BDF file here. So I come up here to the new file, create a block diagram schematic file, and notice that it is defaulted block1.bdf. So I don't go any further until I name this what it's supposed to be. And it does it for me. It should be named exactly the same as what this is named. So if I say File, Save As, notice that it automatically calls it what it should be called. Okay, Lab1B Second.bdf, and I just say Save. Okay? That way it's done and out of the way. Now I can go ahead and start adding some stuff. Okay, I'm going to go over here and double check for questions. So Steve asks, can Quartus be installed on a USB and run from any computer? Ooh. Oh, boy, I don't know about that. Like if it was pulling from the USB drive, could you install the whole thing? I don't know. I don't know. Try it out and see. I'm trying to think of how if there's any reason why it needs to be tethered to your specific computer. And I can't think of any unless there's something that's in the software that makes sure that the copy that you've downloaded matches like your Mac device address or something like that. That's the only thing I can think of why it wouldn't work. But there's got to be like other drivers and stuff that it's installing. And so, yeah, now the more I think about it, I don't know. Because you would have to update the USB blaster driver on whatever device you were trying to use it on. Okay, so it'd be an interesting thing to try. It may be that during the install process, if you're trying to install it on the USB, that it won't let you write to it, that you have to do it on the C drive. I don't know. All right, so if you can figure that out, let me know, and then I'll stick that in my back pocket. All righty. So I'm going to go ahead and start adding I'm just going to add a component. And so I'm going to double click with my left mouse button, and I could also come up here to the symbol tool, but I'm just going to double click, and this time I'll do how about a NOR gate? How about a NOR 2? 2 input NOR gate. Oh, I know what I'm going to do here. All right, so I'm going to go ahead and also create an OR gate, an OR 2, and I'm also going to create a NOT gate. And it's actually NOT. It's not INV for inverter. It is NOT for NOT. What I'm going to do is I'm going to prove that these two things are equal. If I take this, again, it's click, drag, let go. These two, if I were to put parentheses around this top one, and I put a parentheses here and here, those two logic circuits will accomplish the same thing, because again, the NOR is nothing more than taking the OR and then inverting it. And so that's all we're doing here. We're taking the OR and we're inverting it. So I'm going to have 4 inputs. No, I'm going to have 2 inputs. I'll show you how you can do that. So input 1, or just input. And usually what I do for this is I do a Control-C while it's still selected, click underneath, Control-V. That way I get 2 of them. All right, so what I'm going to do is I'm actually going to pull these down here. I'm going to put this here, and I'm going to zoom in here a little bit. So make this a little easier to read. Move that out of the way. Can I move that out of the way? Nope, won't let me. Can I move this down? Nope. Okay. So again, I'm going to name this 1, 2, 3 A. And that's how many clicks I have to do to select it. 1, 2, 3, and B. And then I also need an output. And I'm going to need 2 outputs here. I'm going to need one for this one. And Control-C, pull it down here, Control-V. Please let me move this over. I may just have to get rid of it. Oh. See if I can inch over here. Pull this up. There we go. That works. So let's call this X. 1, 2, 3. Let's call that X. And this one Y. So I'm using the same 2 inputs. Okay, so this is going to be click, pull, let go here, and then click, let go. Same thing with this. Bring it up to here, let go, click, drag over. Okay, so that is, whoops, Control-Z that. See how it made a little X by that? I went too far. There we go. Okay, and so now I'm going to plug this into here. Now I'm gonna make that mistake again here real quick. I'm gonna just because I kind of blew by it again. So what happens if I do this? Okay, I went too far. So it still makes the connection here, but now I've got this dangling little piece that's underneath essentially, or it could be on top of this. I don't know, but I don't like having that there. And you see that little X. So if that happens, try to select just that last little bit, and then you can right-click and delete it. Okay. So that should indicate that you have 2 things that are connected there. All right. So now one of the inputs of this is going to be A, so watch how I make the connection. I'm just going to go from here, click, drag, and make sure you go all the way through the B. You don't want to make 2 connections here. So I go up. There we go. So there, I see the junction. It gives you a junction here when you have more than 2 things connected, or more than 2 things connected, yes. And so then the other one, I'm going to pull right up to here. Okay, I'm actually going to Control-Z that. I'm going to try to do a bad job here. Oh, they're getting smarter with this. In the older versions, if you went too slow, it would make a connection in both places. It looks like it's gotten a little bit smarter. Okay, well I tried to make it not work right. Anyway, there's my circuit. Okay, so in my waveform analysis, it should be the case that X equals Y. Those should be identical to one another. But before I even get over there, I have to compile this and make sure that I didn't make any errors. So I'm going to go ahead and hit the compilation button. It says it's been modified. Do you want to save your changes? Yes. And again, if you can get past this first part with 100%, then more than likely everything else will cooperate. Again, this is the first time I've done this, and so, the first time that you compile a new circuit, it always takes a little while. Then it gets its act together and starts going. Plus, again, my computer's, like I said, it sounds like a jet engine trying to take off right now. It's an awful lot of thought for such a simple circuit. I know I use 3 gates, but come on. What if I had 50? This might take 10 minutes on my computer. Let's go check the chat. Nothing new in the chat yet. All right. Are we going to do this any quicker, or is it just going to take a while here? If you have any questions, now would be a great time to ask. Oh, we're finally down to the EDA netlist writer. Okay. All that to tell me, hey, you still have 14 things that we're going to warn you about. But the big thing here is I have no errors, and that's what I'm looking for our purposes. So I always like to close out of the compilation report when it's done. So now I'm ready to go ahead and set up a vector waveform file to simulate this circuit. So I'm going to come back up here to New File. And about 3/4 of the way down, you see this university program, VWF. Click OK. All right. Now, as I said before, notice that the default name here is waveform1.vwf, okay? If I go File, Save As, I just leave it as waveform because that's what it's looking for in the simulator. Remember, I had an issue with this because I typically like to name this whatever my BDF file is. Don't do that in this version of the software, okay? There's a way you can set it up to have another type, but it's just easier to leave it, as long as you are in your own folder for the lab, just leave it as waveform, okay? So I'm just going to say save, okay? I don't know why it jumped back out to there, but okay. So now I'm going to right-click in this white area, say Insert Node or Bus, go to Node Finder, and this should be blank. The default should be pins all. If it's not, go ahead and select it, and then you want to say list. Now these are all my inputs and outputs. I'm going to pull all of them over at once, and I hit the double arrow. Okay, you can do them one at a time if you'd like. And then you can also pull them back one at a time or pull them all back at once. Okay, so I'm going to go ahead now and say OK twice. OK, OK. There they are. Notice how my outputs, and you can see the difference. I'm leaning in here. You can't see me lean in, but this says input, input, output, output. And notice there's a different symbol for each. So the outputs you always want to leave as hash marks because we don't know what those are. We're gonna let the computer tell us what the outputs are based on these sample inputs that we create. Okay? Now for me, I always like to come up here and say edit grid size, and I like to change this to 50 nanoseconds because I think it's less cluttered. And then what I usually do, if I have, I usually start my inputs at 50 nanoseconds changing. And so, we could even do 100 for this one. Let's do one with 100 just so you can see the difference. So I select my input. I come up here to count value. And I say I want to transition, instead of every 50 to start off with, I want to do one every 100 nanoseconds. And remember, the total time it takes is from 0 to 1 microsecond, a millionth of a second. These are all down in the billionths of a second, nanoseconds, right? So there's my first signal. My second signal here, I'm going to select my input, go to count value. Now this one, I'm going to double it and go to 200. So even though I doubled both of those, you can see by 400 nanoseconds, I've already got all the combinations covered. 0, 0, 0, 1, 1, 0, 1, 1, and then it repeats. Okay? So this goes like 2.5 times if you do it that way. I mean, we could even do it 200 and 400, but it's good to see it repeat a couple times just so you know you're on the right track. So I think this is ready to go. Let's come back up here to the simulation. And again, this is where you would change it. It's looking for this right here, see? All right, capital waveform.vwf. All right, so I'm going to go ahead and go to run timing simulation. Do you want to save your changes? Yes. Boy, this one's taking a while too. Mercy. There we go. So the first thing I notice is that X and Y are the same. So that's good news. Okay. And so that proves my point about the NOR functions being the same. Now let's walk through this and see the actual NOR function here. So 0 and 0. If you OR those together, you get a 0. The inverse of that is 1. If you OR 0 and 1, you get a 1. If you take the inverse of that, you get a 0. And I guess for this one, we could even go further here. Sorry about the getting sidetracked here. I can move the grid size to 100 nanoseconds, and then it lines up perfectly with our transition, so it's even easier to read. So essentially, the grid lines are just for your benefit only. All right, they don't perform any other function. Okay, so now we have, if you have an OR of 1 and 0, you get a 1. The inverse of that is a 0. When you have a 1 or a 1, that's a 1, and then you invert that, you get a 0. So it looks like it's working. Okay. Any questions? All right, so at this point, I would say, all right, I'm happy with my file. I'm confident that it's going to work because I've tested it out here. And so now what I'm going to do is I'm going to go assign pins and go ahead and download this to the board and then try it out. Okay? So that's what I'm going to do. I'm actually going to get rid of this. I'm going to also, I guess I don't have to, but I'm going to get rid of my simulation editor because this is saved. I don't need it right now. I want to pull up this, and this is the PDF that's for the board that we have. And so I'm just gonna jot these down, and I'm gonna jot them down the right way this time. I'm gonna use, let's see, if I look at the board here, I want to use the ones on the far right. So I'm using switch 0 and switch 1. So I'm writing down switch 0 is pin C10, and then switch 1 is C11. That's easy enough. Now, I also want to use an LED, and this is where I made the mistake last time. This is A8 to use the very first one. So this time, John, we're going to write down A8 and not A5. And that is LED 0. Okay. I guess we're going to need another one, right? Because we need another output for the second. You know, we have one for X and Y. So I'm also going to do LED 1 and assign that to A9. All right. Let's come back to Quartus. Super simple. Come up here to Assignments, Pin Planner. Now, there's probably some people out there that know where all the stuff is, and so you could potentially select your input and then go pick out the right, you know, just go straight to it if you knew the board intimately. But I don't, and so I'm going to go over here to Location, and the first one was C10. So one of my inputs is C10. Notice how I only put in C10, and it goes ahead and puts the pin in front of it, and I just hit Enter. Okay, now the next one is C11, Enter. The next two are my outputs. So the first one is A8, and the next one is A9. Okay. Now you can see that it lit up those parts of the board where you're making the connection. So if you just wanted to know where those were at, okay. So anyway, once you're done with this, people always get confused because they feel like they should save something, okay? Go ahead and get out of it. It's not going to lose those. You can see, I'm going to have to zoom in a little bit. You can see that now the pins are assigned, so it's not like they've been lost. However, to lock them in, to be able to program, you need to compile it one more time. You have to lock in those addresses. So again, I'm going to hit Start Compilation. Now, nothing has changed, so hopefully this thing breezes through some of those first, you know, initial sections there. But we'll see. Maybe asking too much of my poor little computer. Okay. All right, now just blast through all of these. While that's doing that, I'm going to come back over here and assign my let's see, how about we use this one. Remove it. Okay, looks like everything went as planned. All right, so let me go ahead and get that down. So that's ready to go at least. Okay, so I'm going to go ahead and close that out. And I went and got my little USB camera here. All right, now that I've got this ready to go, I want to hook up my board. Okay. So got my board, and I've got my USB blaster cable that came with it. And so for me, I'm going to have to get rid of this capture card input so I can make room for this. I'm going to plug it in. And then as soon as I plug this in, whoops. That's right side up. There we go. Okay. And there it's doing its little demo. Okay. Go back over the desktop here. And I want to come up to the programmer, and it's the one that looks like little, it's no longer bacon. It looks like it's red, white, and blue. I don't know what it is. But anyway, that's the programmer. And so you go ahead and click that. And again, The reason why it wasn't showing up on my hardware setup last time when I very first did this is because I had to update the driver. I go through that part of it as well. So if you go to hardware setup here, if it says nothing, okay, if it says no hardware and it doesn't show USB blaster that's available, you have to go update that driver. So go back and look at the, I think you got to do the running your first Quartus. It's the second one, not the install one, but the second one, okay? Let's see. Okay, so now that I have that squared away, I know that this USB blaster is good. I go ahead and click Start. All right, now, when that happens, okay, right now you see that those two lights, those two lights are on, okay? And that's based on these two switches down here. That's S0. And that is S1. All right, so if I push them both up, okay, so now both of them are up. Now notice the other ones are kind of like in a standby mode. If you don't, like I said, if you don't like that, you could write all of those outputs to ground if you wanted to, and then they would just all be off. But the first one is the only one, the first two are the only ones we're looking at. So there's 0, or here's 0, 0 on my switches. Okay, I keep going out of frame here. Here is, I'm just going to do the first one. There is 0, 1. The light turns off. The other way I would check it is then go to 1, 0, where the second one is up. Okay, notice that is off. And then finally, when I go to 1, 1 situation, it's off as well. So it looks like it's working properly. The NOR gates, both of the NOR gates that I created. All right. Any questions on that? Pretty straightforward, I think. All right. Let's crank it up a little bit, and I'll go ahead and preview something else. Okay? Since I got you here, why not? I'm going to go back to, let's see, am I on? Yes, I'm on desktop here. Okay. It's funny, when I have my OBS pulled up, it'll just keep, you can keep following it out to infinity. So when I'm in this mode, I don't know if it's actually doing what I want it to do, so because I can't see. But anyway, let's come back to Quartus here. I'm going to get rid of this. So I'm done with this. I get out of it. Come back to my BDF file. Okay. So what do I want to do here? Maybe I create... I know what I can do. I'm going to come in here and I'm going to delete some of this stuff. I'm going to delete that and delete that. Actually, no, I don't. I want to keep that. I want to get rid of all of this wiring here. Delete. Okay. Now what I'm going to do is, this is kind of a preview. And I'm going to use the same. So I'm going to get rid of this second input here. I don't need this. Delete. Okay. So I'm actually going to pull this down. And what I'm going to show is, make that connection. So all this is going to do is invert A. So Y equals A prime, essentially. I'm going to pull I'm going to short these together here, so I'm going to have them only come. Let's see. I want to undo that real quick, and I want to pull over to here. Okay, and then what I'm going to do is I'm going to pull from here to here. That's better. All right. So I'm sending A through this NOR gate. Okay, and I'm going to see how that affects these two things. All right. Let me go ahead and compile this. So again, I'm now locking in this different schematic here, and I don't have to start a new project file to do it. But of course, it's changed now, and so it's probably going to take it a second to analyze and synthesize. Boy, thanks, Quartus. You created a lot of dead air. Okay, almost done here. And finally, the netlist writer. All right, very good. No errors. So I come back to here, and I want to point something out, okay? If I were to do something like this and ask you to have both inputs be connected to one single input, that means there's only two combinations, right? Because if A is 0, then what's on the input is 0, 0. If A is 1, then what's on the input is 1, 1. So there's only two possible outcomes of this NOR gate, right? So think yourself through that. What happens if you have 0, 0 on the input of a NOR gate? Well, 0 or 0 is 0. If you invert that, you get a 1. So if you have a 0 here, you get a 1 on the output. What happens if you have 1, 1? Right? So if A is 1, that means you have 1 or 1, which gives you a 1. If you invert that, it gives you a 0. So if A is 1, this becomes a 0. That looks an awful lot like one of these. So this kind of steps into the idea of the universality of NOR gates, okay? Just by sort of manipulating the way it's quote-unquote intended to be used, okay? So what we should see here, if I now go to, if I want to bring that back up, the waveform file, I go to Open, and in this, you know, it's going to be here where your BDF is. So it says that I'm in output files here. You have to back up to here where your BDF is, and then you have to come down here and say all files so that it'll show it. Okay, so now I can open this vector waveform file again. I don't have to make any other adjustments to it, okay, because I still just have, let's see, what do I have here? I can get rid of the B right now, actually, because I don't have a B input anymore. So I can just select that, right-click, delete. Or my delete key doesn't work because I spilled something on my keyboard, so I have to right-click and delete everything. But anyway, so now this reflects that we have an A, X, and Y. So that's the only thing I need to do here, and I can go ahead and say, run timing simulation. Yes, I want to save it. Okay, looks like X and Y are identical. And you see the function is an inverter. And so it's true in every case. Okay. Now, if I wanted to go ahead and test that out, I would go ahead and close those down. I've already got the pins assigned, and I already compiled it while the pins are assigned, so I don't need to do that again. All I need to do is go up to my little bacon square up here, and okay, it has my hardware set up already here, so that's good. If this says no hardware, you're going to have to go into hardware setup and then select your USB blaster. Okay? And so I'm just going to go ahead and click start. Now, switch back to my camera here. Okay? With those two pins, those bottom two, right? It's just the one switch, right? I just have the one input now. But it's turning both those outputs on and off. So that's low on the switch, you can see. That's high, and it inverts it, okay? So both of them are performing the exact same function. If you told me what is behind LED 1 and LED 0, I would say there's some kind of inverter, all right? Any questions? No questions. Okay, well, I'm going to do one more thing, and then you are free to go, okay? I'm going to come back here and jump back in. I'm going to get rid of my programmer because I'm done with that for now. Now what I'm going to do is I'm going to double click here. I'm going to add a NAND to and put it right here. Then I'm going to grab an output, Control C, click, Control V, and this one's going to be Z, output Z. I'm going to do the same thing. I'm going to come down here and I'm going to tie into that signal. So I'm doing the same thing I did to the NOR gate, but now I'm doing it to the NAND gate. All right. Now, since I've added a few things here, and because now I have another LED, before I compile, I might as well go ahead and assign that pin. So I'm going to come back up here to Assignments, Pin Planner. And now I need one for my, oh, you know what? It's not going to list it because I haven't compiled it yet. Oh, you got me. You got me. All right, well, let me go ahead and compile this then. Yes, I want to save my changes. So before I do anything, if you're still following along with me, what's going to happen if you only have one input on these two? That means you're only going to get 0, 0 or 1, 1. Those are the only two possibilities if it's the same. Okay. It's thinking awfully hard. All right. Now smash that timing analysis on the net list. Okay, there we go. I'm going to go ahead and close this out. And I'm going to go back to my vector waveform file. So again, if I want to pull it back up after I've closed out of it, you can see, go to Open File. I'm in, oh, look at all these output files. That's not where I want to be. I want to be up here, one file above. And so now there's my vector waveform file. Pull it up. And now I've got 3 outputs. So I actually need to go here, right-click, Insert Node or Bus. Now this one, when I go to List, I really just need to pull this one over because that's the only one I'm missing. So I'm just going to pull that single one over, then click OK. All right, so now I've got the 3 together. All right. So before I do this, I'm going to come back to my BDF here. If you have 0 and 0, that gives you a 0. Invert it, that gives you a 1. If you have 1 and 1, that gives you a 1. Invert it, it gets you a 0. So what I'm pointing out here is this should accomplish what the other 2 things are accomplishing. These 3 should be identical to one another. Okay? So let's go ahead and simulate that. And this is the shortcut for the timing simulation, by the way. And there we go. All 3 outputs are identical. All right. And so then finally, if I said, okay, well now I want to go ahead and download it to the board and see if I can get 3 of them to work. If I go back to my PDF, the next one is A10. So I'll just use the one that's next to them, A10. So I come back up here to Assignments, Pen Planner, and there's my Z now. Now I can say A10, enter. Okay. Now it's assigned. I have to compile it again. So now it's incorporating that extra input in there and all of this logic that it's creating, the instructions that it's creating. Okay, now I'm going to go up here to the programmer again. Everything looks good. I go ahead and hit start. It's been written to my board. There we go. Again, I just have the one, oops, wrong side. I just have the one input, okay? Try to keep my hand steady here. So up, it gets inverted to a low. Low gets inverted to a high. There we go. Now I'm doing a railroad crossing. Okay? Any questions?